from stuff we've covered so far, similar to problems in the notes, which is due next week, Monday. Okay, so let me first recall some things from geometry that we need. So we have a Riemannian manifold. So maybe the first theorem whose proof I'm sure you haven't seen before is the following. As usual, we assume M is complete. Otherwise, you can do anything. Do you know that every manifold has a metric of constant curvature? Every manifold has one, if it's non-compact. Because I can construct metrics which aren't complete. If they aren't complete, I can do anything I want to. So completeness, which you always assume, is certainly should be the beginning point. Otherwise, you can't do anything. Yes. Of course, they're very, very non-complete. Okay, part A is that I of M, so isomorphic group, that's the notation I'm going to use. So set up all F diffeomorphisms, which preserves the length. So isometries. This is a Lie group. And that's non-trivial. That's not quite elementary to prove that. Part B is that if M is compact,
Isn't it finite dimension?
it's finite dimension. Yeah, finite dimension Lie group.
For any M?
For any M. Any M. It's always finite dimension. So Lie group in that sense, right? So finite dimension. If M is compact, then the Lie group is compact, then the isomorphic group is compact.
So the algebra is the
Set of killing vector fields, right? So okay, maybe I should write on the algebra of I of M is a set of X vector fields on M. So in which version do you know what something is a killing vector field? There are two different versions. One can define it. What's the definition of a killing vector field?
If you already have a connection,
I have a metric, so I certainly have the Levitz-Utah connection, right?
you can form the derivation with respect to some vector and projection, and that will be antisymmetric.
Right. So nabla, say, Vxw is minus nabla Wxv. So in other words, nabla x, the cone derivative is q. Of course, remember that this only depends on the point, the vector on the point, so it makes sense. Whereas here I need to know the vector field in a neighborhood. What's the equivalent way of is by isometries. Right. So this if and only if the flow phi t of x is by isometries. Right. That's the equivalent definition. This is more geometric. Right. Flows by isometries. That's what I mean by killing vector field. And in that sense, it's kind of clear that this should be the Lie algebra of the isometry group. Those things in the Lie algebra, the flow lies in the group, so it must be isometries. And then exercise is to show that this is equivalent to this condition on the vector field itself. Okay, so if M is compact, I of M is compact. And in general, so even if M is not compact, for all points P in M, I M sub P, so a stabilizer, is compact. Without assuming M is compact, right? So here M is just complete, and each stabilizer must be a compact subgroup of this Lie group. Right? This actually has a very nice proof, which I'm going to do a little bit later on, because we have to do something which at the same time more or less proves this here. proof of B is similar to proof of C, so these are the easy parts. The hard part is to show it's a Lie group. Okay. This is in Kobayashi no Mizo, volume 1. Not that many books do that. It's kind of annoying to prove that. Okay, so that we're certainly going to assume the asymmetry group is a Lie group. Some other notation or conventions. Let's see which are. Okay. So also the standard notation I'm going to use is a set of balls, a ball in a manifold, right? This set of Q in M. The distance from P to Q is smaller or equal to epsilon. So this I mean closed balls, right? And this is a normal ball. If the exponential map is a diffeomorphism from an epsilon ball in tangent space into an epsilon ball into the manifold, it calls it a normal ball. Right? What else? Don't need that much yet. The isotropic representation I should mention. So if M is homogeneous, say G acts transitively, so then as we already discussed at some point, I can write M as G mod the stabilizer, right, just by sending a coset GP into G times P. This is a diffeomorphism where GP is a stabilizer. On G mod the stabilizer, I have left translations. So if G lies in G, I can call this again LG, although I think before we only used it on the group itself, which is just the action, right? So say K times GP goes to GK GP. Right. And with respect to this map here, let's call this pi. Then pi is what is called equivariant. In the sense that if I first act with left translation on a coset, this then goes under this. This is equal to pi of that is equal to G acting on P, G acting on pi of the coset. So in other words, whatever I do here with left translation, exactly what corresponds to over here with the group action on the manifold. Right? And then for GP, GP acts on the tangent space of P via what's called the isotropic representation. So if I have an element, let's call it K, in GP, I can look at left translation by K from M to M. Of course, LK then fixes a point P. So derivative of LK at the point P goes from the tangent space to itself. So it's, in other words, an element of the endomorphisms of the tangent space. Because if G acts by isometries, then the derivative of these isotropic representation lies in the orthogonal group of the tangent space. And what's also special for us, for an action that acts by isometries, and if the derivative of LK at the point P is identity, this implies that LK itself is the identity as a map from M to M. So the way one says this is that, another way to say this is that the isotropy representation is effective. Right? So nothing in this representation of the tangent space here can act trivially. So the kernel of this homomorphism, if you want to, you get a homomorphism on GP into the endomorphisms of TPM. That's clearly homomorphism. And what this is here, that this is injective. So G isometries implies this is injective. Often called a faithful representation or the group. Why is that?
This is the type of argument that we take the set of the points who are fixed and prove that it's open and closed.
Yes.
I don't remember very well.
But there's a general fact behind this. Which one proves with this what you're saying? What's the general fact? That one is something one should remember, the general fact.
Two isometries are equal and at one point and its derivatives are equal. So the isometry.
That's right. So if f of p is equal to f of q, g of q, g of p, for some p, and the derivatives are the same, this implies f is equal to g. You use it by using the exponential map. Someone takes geodesics to geodesics. So if they are the same here in every geodesic, along every geodesic they agree, the two maps f and g, because they take geodesics to geodesics, and the tangent vector isn't changed. So that's the argument why it's open, and then use a similar argument why it's closed. Anyway, this is a certain important fact here. Summaries are determined by what they do at one point and what they do at one point. Of course, here in this case, we're looking at the ith representation, so the element key fixes a point P, and its derivative then determines it. Right? So this is an effective representation. In general, that's not true. So maybe as an exercise, look at the homogeneous space, which is, say, GLN, R divided by GLN minus 1, R. Here, the isotrope representation is not effective. So it's a homogeneous space, right? I can view this as a group fixing a point. I can let it act as by the derivative on the tangent space and claim that's a highly ineffective representation. Kind of surprising. Because it means that there cannot be any metric on the space here with this group X by isometries. Right? So for a given homogeneous space G mod H, whether there exists a metric on it where Gx by isometries is a condition. Not every space admits such metrics. And that's the simplest example. Okay. Of course, an indication why you shouldn't expect that is already on the blackboard. Yeah, the isotropy, that is the isotropy at a point, is supposed to be compact, right, by the theorem over there. Right? So it cannot possibly exist, have a metric. And in fact, so something we'll probably see a little bit later on is that if I have homogeneous space G mod H, and H is compact, then there exists a metric such that Gx by isometries. Okay. So it's the same thing, right? This condition is exactly what you need for such a space to have invariant metric. So this isotope representation we're going to use frequently. Anything else I need? I think at the moment probably not. Yeah. Okay, I mean, the only thing I really need from a geometry course is I'm going to use the Cool fields a little bit at some points, and I use constant of curvature. Everything else I need, I'm going to review. Like, for example, I don't know if you know things about the holonomy group, what the holonomy group is and properties of the holonomy group. Probably not. It's not in the standard course. So at some point I'm going to talk about the holonomy group when we get to that. It's actually a very interesting subject in its own right, holonomy groups. Okay, so let's start with the definition of a symmetric space, which is very simple. So M is a Riemannian manifold. I don't necessarily assume that at the point that this is complete. I say that so M is symmetric if for all points P and M there exists an isometry which I will call S sub P such that it fixes a point and its derivative is minus identity at that point. So reverses every vector into its negative vector. Right? If this only exists locally, I say M is locally symmetric. If SP exists on a normal ball, B epsilon P. For all P, again, of course. So if just SP is defined in the neighborhood of that point, then I call the space locally symmetric. If it's defined globally, I call it globally symmetric or just symmetric. Later on, we're going to see that the connection is actually fairly easy, or fairly nice. So later we see M locally symmetric plus M simply connected implies M symmetric. Okay, so you can extend these isometries from local isometries to global one if M is symmetric. Okay. Okay. Elementary properties. Or maybe let me just make another comment that if I make this assumption a little bit stronger, so on each point P, each vector gets sent into minus its vector under such a symmetry. One can think of somewhat stronger assumptions than this. So, for example, one could think of the condition for all. Let's see. For all P comma Q and V in TPM and W in TQM, there exists an isometry such that it takes P to Q and the derivative takes V to W. F of P is equal to Q. So I can map any point into any other point, and any tangent vector at the point into any other tangent vector at that point. So somewhat stronger than this condition here, it says I can map any vector into minus its vector. Right? Or if I assume that I can map any vector into any other vector. So so when P is equal to Q, it says in particular, right, there's an isometry fixes a point that takes any vector into any other vector. Right? That is much, much stronger. This is something then that is too strong, and there's a theorem, which is actually not so easy to prove, that under this condition, M is isometric to one of the following models. So Sn with constant curvature, Rpn with constant curvature, Cpn with what is called the Fubini-Studio metric, Hpn, and a few more. So there are very few manifolds that satisfy this kind of a condition. It's too strong. So that these are the to see that these verify this condition is not hard, but the converse, that's a difficult theorem. Okay. Anyway, so this was just a remark. Did I just erase something? No. Okay. So first proposition is that M symmetric implies M homogeneous and complete. So every symmetric space is homogeneous and complete. That's why I didn't want to assume completeness from the beginning, because it's actually a consequence of the definition. And part B is that, let's see which, not forget one property what I need. Yes. If gamma is a geodesic with gamma of 0 is equal to p, then what the symmetry does to such a geodesic, it just reverses it. So picture is the following. That's in fact the way I think of these symmetries. That here I have a point P, here I have a geodesic gamma. It takes a point T, gamma of T, to a gamma of minus T. In fact, that part I claim is clear. Well, let me get back to that. Let me first state all three statements, and then I'll prove it, because they're all easy. Part C is that if M is homogeneous, and a symmetry S sub P exists for some point, then M is symmetric. So that's the useful property in order to prove that certain spaces are symmetric, that if I, for some reason, I know that it's homogeneous, and often the spaces we look at are clearly homogeneous, then all I have to do is construct a symmetry at one point, and then it follows from that it's symmetric at every point. So part C is for constructing examples. So we do part B first, and that implies A. Maybe I should have reversed the order. So SP is an isometry. This implies that SP applied to gamma is a geodesic, because isometries take geodesics to geodesics. And what are the initial conditions? So let's call this SP of gamma of 0 is, of course, SP of gamma of 0, which is SP of P, but that was P. So geodesic starts at the same point. And what is the derivative of this geodesic? So what's the initial direction of the geodesic? So by the chain rule, and of course this was minus the identity, so this becomes minus gamma prime at 0. Okay. So SP of gamma is again a geodesic with the same initial point, and the initial direction is minus it, which means this must be a gamma of minus T, because this is a geodesic also, and it has also initial conditions. Right? So I think of a symmetric space as something that flips the geodesics at a point, and that's an isometry. Okay. Notice that, say, that maybe puts this condition here also into a better context because this map SP always exists. Right? Take a small normal ball. I can always send, I know what SP is supposed to do. It's supposed to send this point to this point. Right? There's no other choice. SP is well defined locally. Okay. Then the requirement is no symmetry. That's a stronger condition. Right? So that's what is important here for locally symmetric. If it's globally symmetric, I also get some kind of problem of uniqueness. Right? If I go from here to here, maybe I can do that along another geodesic. Then if I go up to minus here and up to minus here, well, these have to be the same points. Right? So geodesics, when they meet again in the opposite direction, they meet at the same point. That's then also a very strong condition. Right? So this here is some kind of global condition on geodesics as well. Okay, so that's B. Part A then follows easily. Let's do the completeness first, maybe. So if it's not complete, that means I can find a maximal domain of definition. So there exists the geodesic gamma, which is defined on 0, say, T0, but not at T0. Okay. Because that means that as I go towards T0, I'm running off to infinity. Right? So I reach infinity in finite time. That's what non-completeness means. Okay. But now I can use so here's my geodesic gamma. So it goes, it's defined. It might run off to infinity, but that's a problem. But I have a symmetry at every point. So let's choose this point to be, say, T0 minus epsilon. Right? So I know certainly up to there is defined. Then there exists a symmetry at this point, gamma of T0 minus epsilon. Right? So this exists, and it takes gamma to gamma. And what does it do? Well, remember, it flips the geodesic. So here's T0 minus epsilon. So if I go a little bit before that, say epsilon before that, then I end up, so this here is T0. Then I end up in so let's maybe go back to epsilon, right? So this will be T0. Let me draw a bigger picture. Here's T0 minus epsilon, minus 2 epsilon. And that means now the geodesic is defined certainly up to what point? So it just flips the geodesic. So here's the geodesic. It just flips this geodesic. Or it's defined as long as this one's defined, right? So actually it's defined up to T0 minus 2 epsilon plus what to do. I want to define beyond T0, right? Okay. So, yeah.
You get up to twice T0.
Yes. I take the symmetry at this point, right? And then I take the point T0 minus 2 epsilon, and this goes into T0 plus epsilon. Okay, because I flip at this point right here. That's my point where I flip. So it's defined beyond T0, right? So hence gamma is defined on 0, T0 plus epsilon. That's a contradiction. Okay. Okay, so it's complete. This also implies quickly that it's homogeneous. We saw it's complete, so I have to prove that given 2 points P and Q, I have to construct an isomer that takes P to Q. Right? And since it's complete, I know by Hopf-Rinoff that there exists a geodesic, in fact a minimal geodesic, though that doesn't matter, gamma from P to Q. Say gamma is defined on 0, 0, 1. So gamma of 0 is P, gamma of 1 is Q. So here's my point P, here's my geodesic, here's my point Q. And to go from P to Q, what should I just do using symmetries? Use the symmetry at the midpoint. Right? So let this be gamma of 1/2. Now look at the symmetry at the point gamma of 1/2. So it takes, like we said, it flips the geodesic at this point. So it takes this geodesic to this geodesic, goes from 0, 1/2 to 1/2 to 1. So this takes P to Q. Okay. So using completeness and Hopf-Rinoff, you just flip in the midpoint and you see it's homogeneous. So that's part A and B. Part C is also easy. So we have some P, so there exists a P and a symmetry at P. Right? And we know it's homogeneous, so of course, homogeneous in the Riemannian sense. Right? M is a Riemannian manifold. Homogeneous means with respect to isometries. The isometry group acts transitively on the manifold. Right? That's what I mean by homogeneous here. So if I have another point in M, I want to construct the symmetry at the point Q. So what do? Well, I use homogeneity. I can go from P to Q. Right? So there exists F in I of M such that F of P is equal to Q. And what should the symmetry at Q be then? Conjugation, yes. Let's see, in SP, do I put an F inverse? I want to go, yes, F inverse goes from Q to P, and then I go from P to Q. Right, I claim that's the symmetry. So let's just quickly plug it in. It's kind of clear that's what's supposed to happen. Right, I apply F inverse. That gives me the point P. Right, F goes from P to Q. That's equal to P. So that's F of P, which was Q. So that's clear by construction. And the derivative works out nicely because of the symmetry property. Point P again. Because this was minus identity, right? That's our assumption. So it's minus dFP composed with dF inverse at Q, which is minus identity. Okay, so just conjugate, and I get the symmetry at every point. So I just have to write one point. Okay, so these are elementary properties of a symmetric space. Let me maybe start with some examples before I go on to the next result. First, there's some very easy ones. Space of constant curvature. So I claim Sn, Rn, and hyperbolic space Hn are symmetric. And it's kind of clear how to do that. Say, let's do it for Rn. What is the symmetry through a point? So P is a point in Rn. V is another point in Rn. What should that be? I want to flip in the point P, so that's the formula. In fact, here I have I have a symmetry that takes any vector into minus its vector around the point P, right? So what's the formula? P minus V, P plus V, something like this? Or maybe V minus 2P, something like this. Let's see. If I plug in P here, 2P is opposite. If I plug in P for the vector V, I get P, so it fixes a point. And if I differentiate, this is linear in V. It's a linear summand. If I differentiate it, minus identity. Okay. Okay. So that's just a summative for Rn. For Sn, there's a similar formula. Now it's not quite the same. So, of course, P and V are both points in the sphere. So now, which way should I think of it? Use my point P. I want to see what does it do to another point on the sphere. So both these have unit lengths. It should, of course, flip it to the other side, right? And what is that? I claim if I look at the line going through that point in 3 space, it's reflection in that line. And the reflection in the line would take this vector to minus its vector. Takes this vector to this vector, right, reflecting in this line. So I want to reflect in this line here. And this would be exactly what I would get if I go along a great circle here. So there's a nice way to write this down, which of course I forget. It's useful to have the explicit formula, so we can do it also in hyperbolic space.
This is a rotation of pi around this axis defined by P. Is it?
No.
190.
That's minus identity in the orthogonal complement of the line, right? Which is the same thing as reflection in the line. That's right. That's right. And to write down explicitly, it's minus V plus, I have to project 2 Vp times P. And that's how I project onto the orthogonal complement. Notice that when V is equal to P, right, they're both of unit lengths, so I get minus V plus 2V, it becomes V, right, it takes V to V. It's linear in V. So why is ds P applied to a vector, say to a vector, say x, equal to minus x? It's linear in V, so I differentiate just that it's linear map. Here I get minus identity. Here I'm supposed to get 0. Why would I get 0 here? So this here is supposed to lie in the tangent space at the point P of the sphere. That means that x comma P is equal to 0. So if I differentiate this part here at 0 because I'm in the tangent space of the sphere. Okay. So I can think of this as a projection. But now that tells me also how to do it in hyperbolic space. You can write down explicitly. If I take the right model of hyperbolic space, So here I take what's called the Lorentz model. You know the space, this model of a body space? So one model is upper half space model, which is what one usually starts out with, but I think there's a more convenient one. Exactly. So here I look at Rn plus 1, or often written as Rn comma 1, with respect to an inner product that has signature, right? So x comma y is equal to, say, summation xi yi 1 to n minus xn yn. So a signature 1 comma n. And in that I look at the unit sphere. So I look at those vectors in Rn comma 1. And now it turns out to be, the question, do I set it equal to minus 1 or plus 1? Of course, depends on my choice of signs here. Yes. So it's a unit sphere, but the inner product is more, of course, this is an indefinite inner product, right? So there's zero vectors of zero lengths, positive, negative lengths, right? So I look at the unit sphere, which has radius minus 1. So if you want to write down a model, what does zero lengths look like? That's a cone. Right, this is equal to this squared is equal to sum of those squares. That's a cone, and then minus 1 is the space in here. So the picture tells you also I should put in another condition. That's not quite hyperbolic space because it has two components, right? There's something below it also here. This also has length minus 1. Right? So I also add to that the condition that xn is positive. Of course, here I have n plus 1. This should be the n plus first coordinate. Right. It's supposed to be Rn comma 1. And so now I can write down the symmetry in the same way by just changing something. So as P of V, I claim should be minus V minus 2 Vp comma P, accounting for the fact that P comma P has length minus 1. So right here, so both P and V have length minus 1. Okay. Because for that I need this so that V is fixed, so that the point P is fixed. Right? This will be minus P, and P comma P is minus 1, so it's plus 2P, so P goes to P. So making that little change, it works as before. Of course, I have to check something. I have to check this isometry. It's linear in V, so I know how to compute the derivative, so that's not hard to check its isometry. Okay, so these are the simplest example. Manifold, constant curvature 1 manifold, which are simply connected to all symmetric spaces. An exercise which kind of points out an issue in general, that what if I take a quotient of those constant curvature manifolds? So any space of constant curvature, which ones are symmetric? Okay. If I do this for the sphere, so take a sphere of radius 1, divide by gamma. Gamma sits inside the isometry group and acts freely. So in the quotient is a manifold. Again, there's constant curvature 1. This is symmetric if and only if the group is just plus or minus identity. Then, of course, Sn mod gamma is Rpn. So that's the only quotient that's symmetric. Okay. It's kind of surprising because there are certainly many such groups which act freely. Right? But notice, of course, these are all locally symmetric. right? Because I have a covering, which is a local isometry by construction, right? So certainly you have local symmetries because I have them upstairs. I get local symmetries downstairs also, right? So here, this issue arises I mentioned earlier, is it well defined globally? Right, this property, if I take a geodesic cone from this point to this point, if they aren't unique, if I continue on the opposite direction, do I come back to the same point or not? So the exercise is to show that this only happens if the group is like this. For Rn, not quite sure actually what the complete answer is, but certainly as an example, Rn mod Zn, so an n torus, is symmetric. So there it's not hard to see that things work out. Not sure what all the flat manifolds are that are symmetric. That I'm not sure about. It's maybe a good question. What flat manifolds are symmetric? This will be the question. Besides the torus. It could be there aren't any others. Well, of course, I wouldn't have to divide by full lattice here, so maybe I can divide by a lattice of smaller dimension, so like a cylinder, right? So I could divide by Rn cross, say, Zm. This would be an M torus cross a Euclidean space of dimension n minus m, like a cylinder. That should also be symmetric. But this may be all of them. Of course, so this also, say, raises an obvious issue. If I have two manifolds, if they're both symmetric, then the Riemannian product is symmetric. So Riemannian product meaning the metric on the product is also the product metric. Right? Because what's the symmetry around a point P, Q? Well, it should be the symmetry in each point, each component. Okay, that's kind of clear. That's the symmetry. So products of symmetry space is certainly unsymmetric. Let's do one example that's more complicated, more interesting, less trivial, which is the Grassmann manifolds. So k-planes in Rn, or k-planes in the complex n space, or k-planes in hyperbolic n space. These are all symmetric. So here I could actually also add something else, because k-planes in Rn, that's actually not simply connected. What else can I add to a k-plane to nail it down a little bit more? I could add an orientation. So, and that usual notation is then GK0Rn. This is the set of oriented k-planes in Rn. So we have fixed the usual orientation Rn, right? Then I look at the k-planes which also have associated an orientation. Because there are two choices, right? Plus and minus. So it should be like a two-fold cover. Where I just forget the orientation. So that's the forget the orientation map, a clear one. And since there are two choices, this is a twofold. two-fold cover. So I could add the oriented ones here if I want to. Here there's a natural orientation coming from the complex structure. So here I can't do that. And similar here, that's also natural orientation. So one thing one can prove, I'm not going to do that now, is otherwise they're simply connected. These are all simple connected manifolds. And of course, this one has pi1 equal to Z2. Yes?
And that also is symmetric.
Yes. Yes.
We could add the
Stiefel manifolds are not symmetric. Yes. So, what's that? Remember, I think VK was our notation for Stiefel manifold. So K-frames, as opposed to plain K-frames in Rn. This is not symmetric. Of course, you even have to ask the question, what metric do I put on it? So with respect to which metric do I claim it's not symmetric? Right? There aren't that many choices because we know that if there is a metric that's symmetric, it must be homogeneous. So among the class of metrics I would want to consider on this kind of Stiefel manifolds are only homogeneous ones. Okay. That still gives you lots of freedom, but certainly something that's controllable. And among those one control, it's not symmetric. I think a little bit later when we derive more results, this will probably be easier to see. Right now, this would be hard. That's correct. So this, what quotient is this?
ON under O minus K.
Yes. Right. Isometry acts transitively on any n frame, they have a k frame, and the stabilizer with minus k. Whereas for the Grasser manifold, what do I get for the Grasser manifold?
One more quotient.
Okay. So here it's a stabilizer of the first k coordinates. Right? Anything that's transitively here, and this is a stabilizer. Anything in the first k coordinate, anything orthogonal to that gives me the same k plane in Rn. Notice there's something different between this and this here. I could rewrite this a little bit. Not only does ON act transitively, but also the identity component. Right, so these groups are both not connected. It's often nicer to write it as a quotient of a connected group. What's the stabilizer?
SO minus K.
Right, so how do I imagine the stabilizer to be? Here is ON minus K. Right, for that to have determined 1, the lower block must have determined 1 also. If I do that here, I can also do it for planes then, of course. What's the stabilizer now? Is it SOK cross SON minus K? Not necessarily, right? So here, my matrices look like 0, 0, A, B. A lies in OK, B lies in ON minus K. The only condition I have is the determinant is equal to 1. So as long as det A and det B are both minus 1, you're OK. So the way one writes this is S of OK ON minus K. So where this S here reminds you of the determinant is equal to 1. So in other words, it's a set of all such matrices, A0, B, such that det of AB is equal to 1. That's what this here represents. That's a convenient notation. Notice this group has 2 components now, right? This has 4 components here. This has 2 components. Well, see, it's connected. That kind of indicates already that this space should not be simply connected because I can do the following. I can just look at the map which sends SON, SOK, SON minus K, which is the identity component, into the Grassmannian over there. Right, we're sending, say, let's look, G times a coset goes to G times a coset. But now this is a coset with respect to this group. So maybe so coset goes to coset. But this has two components. There's one component. What's a two-fold cover again? So this space can't be simply connected. Indication is already that the stabilizer is not connected. So this would be general statement. If I have a homogeneous space and the stabilizer is not connected, but G is connected, then the manifold can't be simply connected, because I can write down a map like this. Okay. Of course, here the stabilizer isn't connected, but G also wasn't connected. Then it's not true. So I'll come back to such issues later on. And of course, this here would be the oriented Grassmannian. This here is a Grassmannian. Right, if I require my plane to have an orientation, A must preserve the orientation, so that is equal to 1. Then that is here is also equal to 1. Okay. So that's oriented and unoriented Grassmannian. I'm going to do one example, which is this one here. These are similar, but just replacing a real inner product with a Hermitian inner product or a quaternion inner product. So first I have to put a metric on this Grassmannian. The metric is almost unique, but the easiest way to write down what the metric is by embedding it into a large dimension Euclidean space. Let's call it V. And V is the following. So how can I describe a K-plane Rn? I could either write down a basis, but then of course it's many different bases define the same K-planes. That's not such a good way to do in general. There's another way to look at it, namely simply as a projection into the plane. So write down endomorphism, so a matrix, which is a projection. So what does it mean to be a projection in terms of matrices? Squares itself. Anything else? And P symmetric. So symmetric matrices whose squares itself. Then I claim P is then simply the projection onto the image of P. Actually, we're going to see. I have to add one more condition. Let's think about this first. So first, why is that true? That P is projection onto the image. What's the easy way to see that? Probably so. Maybe the first statement is that imp is orthogonal to kernel P. Claim.
It must be diagonalizable, and you have that the eigenvalues are only 1 or 0 because you have a.
Yes. And they're orthogonal because it's symmetric. I want this to be an orthogonal projection onto the image, right? It should be an orthogonal projection onto the image. And because it's symmetric, it's also an orthogonal map. And now, okay. You can also prove it without diagonalizing if you want to. Just prove this here by since P is symmetric. and then the P applied to a vector V plus W, well, where V is in the kernel P and W is in the image of P, is equal to W. Right. So it's a projection onto the image, a orthogonal projection onto the image. The equality can't quite be true. I should add something to get the Gauss-Mainian. I should add one more condition. The rank. But otherwise, I get any plane, no matter what the dimension is. I want to somehow add the fact there's dimension k. The rank is one possibility. Even better than that, because easier to compute would be the trace. Right? So I would require the trace is equal to k. Again, if you think of the eigenvalue 0 and 1, then the eigenvalue 1 eigenspace has dimension k, and that's what you're projecting onto. So this is a so that here now I get an equality, and it sits inside the vector space, which is the symmetric matrices. That's clearly a vector space. Okay. I could add this condition that's also a vector space, but maybe we don't want to do that. But of course, this here is a condition that gives an embedding. That's not linear. Okay. So this is the important condition here. On V, there is an inner product, a natural inner product. So take two symmetric matrices. How would you define the inner product? There's on matrices, in general, on the set of matrices, there's a natural inner product given by the trace of A times B transpose. Right? This works in general. Of course, here it's just P times Q because they're symmetric. So it's the inner product. And then the Gauss-Mainian has an induced inner product. Okay. Notice that even for this is an interesting embedding, even when k is equal to 1. So what do I get when k is equal to 1? That's projective space, right? I've now embedded this into the set of n by n symmetric matrices. Right? What's the dimension of this? N by n symmetric matrices, n times n plus 1 over 2. Right? So it's an embedding of RPn into n times n plus 1 over 2. I claim the metric has constant curvature. Why is that? Maybe we'll use it as an exercise for the moment. In the induced metric, of course. And that's called the Veronese embedding. So for RP2, you send it into RP2 n equal to 3 into a 6-dimensional vector space. You can reduce the embedding, so I could also Okay, sorry. That's not the right dimension. Well, maybe I want to add this condition to the vector space. I could not. It doesn't matter. So certainly I could say, well, the lines inside here sit in the subspace where the trace is 1. That's one more condition. So it sits inside a vector space, say W of dimension n times n plus 1 over 2 minus 1. That's a linear subspace.
N minus 1 dimension of V.
Symmetric matrices?
N.
That's Q-symmetric.
I think it's
N minus 1 is Q-symmetric. Right? You can prescribe the values on the diagonal and anything above the diagonal. Right? Anything above the diagonal is n times n minus 1 over 2. That's Q-symmetric, because then there's 0 along the diagonal. I have to add n more for the diagonal entries. Right? And now one can even show that it sits inside a sphere. So of a certain radius. So the image actually sort of sits inside a sphere. So for example, one gets here, this is digression from RP2 and get an embedding into, so what do we say? This was n equal to 3, so 4 over 2 is 2 times 3 is 6. Sits inside a subset of dimension 5, sits inside a 4 sphere. So this actually goes into a 4 sphere of a certain radius, which I forget. Okay. And that's minimal. And that's usually called the Veronese embedding of RP2 into S4. So very pretty way and complicated way of viewing RP2 or RPN in general. There's a very natural embedding into a very high dimensional Euclidean space, where the induced metric exactly is what you want as constant curvature. Okay, so digressions. Now I want to construct on this. I want to show that the Grassmannian with respect to this inner product is a symmetric space. So maybe if I want to indicate, if I have a subspace in Rn where the dimension is equal to k, how often let PE be the projection with the image equal to E. So if I want to specify in which subspace I'm talking about, just give it a name and call the projection P sub E. I also have another map, namely a reflection. In the subspace E. And that's prescribed by saying that RE of V is equal to V if V lies in the subspace, and minus E if it's orthogonal to it. So reflection is subspace. So I have projections and I have reflections. And the claim I want to make is that, so proposition, if you want to, the symmetry S sub E, right, of the symmetric space, I have to, for each point, I have to construct a symmetry. So take a K-plane, call it E, and I can construct a symmetry around that, apply to a projection. And the projection is going to be conjugation with reflection. So here Q is in fact an element of V if you want to. Certainly a linear map from V to V. Right? So I can view SE as taking V to V. It's linear. It's now symmetry because I'm conjugating, and certainly the reflection is an isometry. So I'm conjugating with isometry, I get another isometry. So this here is a isometry of V, and I claim now that, in fact, it takes the Grassmannian into itself. So I just have to check the conditions, right? What was the condition? It must be a projection. So square it. So that's REQ, RE, REQ, RE. The reflection twice its entity, so that gives me REQ, RE. So indeed the square of that map is itself, that's a projection. And the trace under conjugation, of course, stays invariant. So if Q is a K-plane, then this conjugate is also a K-plane. So now I have a map from the Grassmannian to the Grassmannian, and I have to show its isometry. Maybe before I do that, let me just say, what does that mean geometrically? What does SE do to a plane? You can kind of suspect what it should be. I do conjugating with RE. RE is a reflection in E. So what should that do? I claim it just reflects the plane. So what would that say? What's the plane? The plane's the image. And what's the image of SE of Q? I claim it's a reflection of the image of Q. So this would say that SE reflects planes. So take any vector in Q if you want to, apply the reflection, and that's a vector in the new plane. So in that sense, it's just a reflection in the plane. See, is that obvious? I guess that's what happens when you conjugate, right? If you take any linear map and a conjugate, what's the image? It's like a change of basis if you want to. Right? RE inverse is the same thing as RE. It's also RE transverse. So I can view this in several different ways, right? It's RE, QRE has its own inverse. It's also RE, QRE transpose. So the last one is the change of basis. So it just takes image to image. Okay. So that explains this equation right here. RE is my change of basis formula. So it just reflects planes. So very geometric. Okay. And I think I'm not going to do that now. It's somewhat tedious to check that this is an isometry. Check that so certainly one thing is clear. It fixes the projection which defines the subspace E, because I've put PE here, so this would be RE, PE, RE. What does that do? If it lies in E, R doesn't do anything. E was the image. This doesn't do anything. This doesn't do anything. So from E to E, it's just the identity. And on E perp, RE is minus the identity, and P sends it to 0. So there on E perp, it's simply the 0 map. So indeed, that means that this is a projection onto E. Right? It's 0 in the orthogonal complement. On E itself, it's identity. So it fixes this point, and now the somewhat tedious calculation is that the derivative of the symmetry at E, at the point PE, if you want to, is minus identity. Okay. The only trick that one has to think about is how to write down a tangent vector. Maybe just talk about this, and then I'm going to finish. What's the tangent space of E of the Grassmannian? I can think of the tangent space of the projection, P sub E. So how do I write down such a tangent vector? I would take a curve inside the space and differentiate. Right? So how do I do that? I claim take something of the form P sub E and go some direction.
Aren't they global isometries?
Yes?
And the expression is linear because it's a
Yes?
conjugation.
Yes?
So the image of a vector will be the conjugation of the vector. When we take in a product, we will be taking trace of him against some other one. Conjugation cancels in the middle.
That shows an isometry.
Hmm?
That shows an isometry. Are you trying to argue why this is true now?
Yes. But by taking the native product in the ambient as the trace of one against the other.
Yes. Yes?
So I say, take a vector, conjugate it, that is the image of the vector, that is the differential. No, I'm trying to see why it's an isometry.
Yes, yes. Okay, yes. That's indeed easy, right? If you can give me an elementary argument why this is true, actually I'd be interested. I had to argue a little bit. Particularly you have to understand, I think you have to understand what the tangent space is. So here's the way one can do that. That is what it means to be a projection, right? I can assume PE here lies in the vector space, so it's symmetric. Trace P is equal to K. Right. I add anything in the vector space here, so Q is symmetric. I want to say one is lying in the tangent space. This is my tangent vector if you want, right? I go in the direction of Q. Inside my big Euclidean vector space, I'll just take a straight line, starting at this point, going in the direction of my potential tangent vector. But now I have to understand what does it mean to be a tangent vector. So I take the equation that says it lies in the submanifold, a projection, or differentiate. So when I differentiate, what happens? Because PE squared is P, that's always true, it goes away. Right? If I take the t derivative, I get what? PE times QE plus QE times PE, they don't commute. Right, that will be the t derivative here. The t derivative here, of course, is QE. So this must be QE. I have to add one more condition because the trace must be K. Right, so the trace for this whole thing to be K, because I want to stay in the space, trace of this must be 0. So that's the tangent space. Right? The set of all Q with this property, that's a tangent space. So now that I have a linear description of what the tangent space looks like, now I just plug in and check that the derivative is minus identity. So that now becomes a calculation. Maybe there's an either argument. If you can see one, tell me. I had to crank it out. But, okay. So that's a first non-trivial example of Grassmannian. Later on, after I develop a little bit of theory, we'll see a bunch of other examples like Lagrangian subspaces is a symmetric space. It's a very important symplectic geometry. The set of inner products on a vector space. Look at all possible inner products on a vector space. That's a symmetric space. Set of complex structures on a vector space. That's also a symmetric space. So they're all very natural basic objects that one studies in many different areas, which are symmetric spaces. And then one can try to use properties of symmetric spaces to study these natural objects also. So that's what I want to get to in the next couple of lectures.